All right, welcome everyone to the monthly colloquium. Today we have Professor Arul Lakshminarayan from IIT Madras. First of all, it's nice to be back in sort of an in-person meeting, in-person seminar. We've not had one for a while. This is a hybrid one. So there are participants online as well as people in the audience. For the people in the audience, I just want to mention, if you ask a question, please do use the microphones in front of you. Please unmute yourself on the microphone and then ask the question so that participants online may also hear the question. So with that, I'd like to introduce our speaker today, Professor Arul Lakshminarayan. He's a theoretical physicist from IIT Madras. Arul got his PhD from Stony Brook in 1993. He was then a postdoc and later faculty member at PRL in Ahmedabad. And from 2003, I believe he's been at IIT Madras. He's also held some long-term visiting appointments at Washington State, IIT Kanpur, and the Max Planck Institute for Physics of Complex Systems in Dresden. So his research interests are quantum chaos and quantum information, many-body systems, sort of related areas. And I believe one of his other interests is quantum classical correspondence. And I think today's talk might hit upon similar themes of relationships between classical problems and quantum problems, and also Sudoku, I believe. So he's going to be talking about 36 entangled officers of Euler, a quantum solution to a classically impossible problem. I'll hand it over to Professor Arul to explain all these words to us. With that.
Thank you very much, Michelle. Is this fine? Audible, yeah? Thank you so much. And it's a pleasure and honor to be here giving this colloquium at ICTS. And it's also my first outing in a real situation, so to speak, that it's not an online talk. So this is a work which has been done with a PhD student of mine, Suhail Ahmad Rada, and this is the ex-student gang of Karol Szyszkowski, who's at the Jagiellonian University, Krakow, and at CTP, Warsaw. I said ex because I think everyone there has graduated with their PhD, with one of the chapters being somehow related to this problem of 36 entangled officers of Euler. So just to mention the sources, so this is a paper on the archive, which eventually got published in the Physical Review Letters. There's also a write-up about this, a quantum solution to an 18th century puzzle. But even before this paper got published in the Physical Review Letters, there is a popular article written in Quanta magazine. And there is a much more recent work with this very profound title, 9 into 4 equals 6 into 6, Understanding the Quantum Solution, which you might consult for a more elaborate discussion of this, which is there presently in the archive. Okay, and in fact, this was one of 5 stated open problems for the KCIK Award on Quantum Information, the Polish National Quantum Information Center. Very interesting problems. One of the third one was find solution to the problem of 36 entangled officers of Euler, or show that the solution does not exist. So in fact, this was awarded recently. All the students in the paper were awarded this. So the amount of money which was awarded was the year in which the solution was found. And there was a warning that don't wait longer because inflation will take over anyway. So, okay. So what is the fuss about? Well, our objects really start with these classical constructions of Latin squares, which are nothing but some d by d arrays. Here I'm taking the example of 3. So we have these 3 numbers, 1, 2, 3, which we write in such a way that if you arrange it in a 3 by 3 grid, there is no repetition along a row or column. That's it. And here is an example of a Latin square. So clearly it's something like a Sudoku puzzle, which is more complicated. It's a 9 by 9, and where there is no repetition within 3 by 3 subsquares. Things start getting interesting when you take two Latin squares like so. So these are two different Latin squares. These are arrangements of 1, 2, 3, such that there is no repetition along row or column. Both of them are Latin squares, but they are called orthogonal. They call orthogonal if they satisfy the following property, that if I was to take the entry in one cell and the other cell and put them together, I get 1, 1 from the first and the second entry and so on. So I do this for every cell and I get 9 entries. If these 9 entries here cover all the possible 9 combinations of 1, 2, and 3 as pairs, then this is an example of an orthogonal Latin square. And this is an example of that because you have all the combinations from 1, 1 to 3, 3, and they obviously can occur only exactly once. So that is the definition of an orthogonal Latin square, that there is no, so if we take something like this, there is no repetition along the first or the second entry along any row or column, and they contain within them all the possible D square combinations or pairs exactly once. Now, that was an example in D equals 3. It's very easy to see that D equals 2, it doesn't exist. In fact, there are only 2 possible Latin squares, 1, 2, 2, 1, and the other is 2, 1, 1, 2. And you put them together, you have 1, 2, 2, 1, 2, 1, and 1, 2. And you can see that it does satisfy the constraint that there is no repetition along a row or column in the first entry or the second entry. However, it doesn't satisfy the important constraint that all possible combinations occur. It repeats itself in 2, 1, and 1, 2. There is no 1, 1, or 2, 2. Therefore, there is no orthogonal Latin squares in D equals 2, the simplest, smallest possible example. D equals 3, I just showed you an example, definitely exists. So there are many ways of representing this. So every square, subsquare of this, or cell of this, has 2 data points. So they could be, in this case, the color of the square and the rank of the chess piece. Okay, so this is another representation of an orthogonal Latin square. So there is a king will occur with a different background color in each of these. There are 3 background colors and 3 ranks. So that's a representation of an orthogonal Latin square in D equals 3. 4, it exists. So actually, it's easy to construct for odd numbers these Latin squares by just shifting these symbols around. For example, this is got by just shifting this to the left. And this is also got by shifting this to the left. The colors you shift to the right. So the rank you shift to the left, the other you shift to the right, and then you get an orthogonal Latin square. It's not hard to see that actually you can construct this rather easily for D odd number. D is 4 is a bit more of a challenge, but it is possible to construct, and here is an example of that. 5, as I said, is quite easy. Here is an example of this. 7 is also easy enough. And you can start constructing these. And you may think that this is a simple problem, but you can see obviously a gap at 6. And this is related to this 36 officers problem of Euler. And this was, I believe, a recreational mathematics problem, which was in the air in Russia when Euler was working there. And legend has it that the Queen posed this question to him. It's a very curious question, which has exercised for some time. The ingenuity of many people has involved me in the following studies, which seem to open a new field of analysis, in particular, the study of combinations. The question revolves around arranging 36 officers to be drawn from 6 different regiments so that they're arranged in a square, so that in each line, both horizontal and vertical, there are 6 officers of different ranks and different regiments. So this is exactly the problem which I stated, only in terms of a military arrangement. And what Euler showed, immediately being Euler, generalized the problem to d by d, and he showed that OLS exists for all odd dimensions. He also showed that it exists for all multiples of 4. And he conjectured that it does not exist for 2 modulo 4, that is, numbers of the form 2 plus 4n. So 2, of course, we can easily show does not exist. N equals 1, that is 6 dimensions. He conjectured that it does not exist with extensive calculations or work. But he also conjectured that it doesn't exist for any of this, 10, 14, etc. So Gaston-Terry in 1900 proved using pretty exhaustive methods, but one should understand that these were not just exhaustive, because he has to classify these orthogonal Latin squares, which are very many in numbers, and he didn't have any access to a computer, so a lot of respect for that. Proves in 1900 that OLS in D equals 6 does not exist. So that settled it, but then that gave an impetus to the Euler conjecture possibly is true. So in fact, there were several proofs that were offered for the Euler conjecture till 1959, all of them incorrect. So what happened in 1959 was these mathematicians, R.C. Bose and S.S. Shrikande, showed that an orthogonal Latin square exists for D equals 22. So not for D is 10, but for D is 22, they showed that it exists. And this is of the form 2 plus 4n, obviously, and therefore it contradicted the Euler conjecture. So this was the first sign that Euler conjecture is not true. And so that is R.C. Bose. I believe there's a center now which is started in his honor at ISI. But I believe when this work was done, he was working in the United States. And so this is one of his well-known work. He was notable for his work along with Shrikande, who was a student, and Parker in their disproof of the famous conjecture made by Euler dated 1782 that there do not exist 2 mutually orthogonal Latin squares of order 4n plus 2 for every n. So in fact, Shrikande, he, as I said, so there's a lovely article there's a lovely interview and article in the Wire in 2017. Shrikande died shortly after that. So both Shrikande and Parker showed, in fact, that OLS exists in all dimensions except 2 and 6. In particular, they displayed an explicit example for the smallest case of D is 10. So let me try to argue as to how do we classify these orthogonal Latin squares. How do we identify whether some particular I mean, it's easy for us when we look at something to identify it as an orthogonal Latin square, but you really need to do the work in that. So what is the mathematical basis for an orthogonal Latin square is something which I would like to go into now. First of all, yeah. So let's look at this. So we're going to associate with each orthogonal Latin square a permutation matrix. Okay, a permutation matrix is a matrix of 1s and 0s such that every row has exactly one entry, which is 1, everything else is 0, and so also every column. So we're going to associate a permutation matrix to every Latin square or orthogonal. Well, they're going to first of all see whether there is some combination of this is in fact an orthogonal Latin square or not. But what we are going to do is we're going to, let's say we just arrange all D square possible pairs of numbers into these D square cells in a D by D array. Then it is a particular permutation. It corresponds to a particular permutation. That is clear because you have all the D square in a D square cell. For example, if you had 1, 1, 1, 2, 1, 3, 2, 1, etc., till 3, 3 here, you may think of it as an identity permutation where the address of the cell is the entry of the cell. Okay, so let's start from that. So in fact, let's look at this bijection of row and column to entry 1 and entry 2. Okay, so this is an address of the cell, which is the row and column. For example, this 3, 1 is in the second row and second column. So that would be the row and column, 2, 2, and the entry is 3, 1. Okay, here is an example of 2, 1, so the second row and the first column, that is the entry is 2 and 3. Okay, so this is the bijection which we get. Now, we can do the following. What actually distinguishes an orthogonal Latin square from something which is not an orthogonal Latin square is the following, that we can specify another square of this kind by specifying just the row and entry. Okay, so, well, let's just go through this. Because every row and column, that is the address of it, specifies uniquely for you the entry 1 and entry 2, you can give any 2 of them rather than all 4 of them to identify the other 2. Okay, so here is an example of that. Here we give the row and entry 1 and ask what is the column and entry 2. So if we specify the row, let's say the second row, and we say that the first entry has to be 2. Okay, the first entry is 2. So we look at this and we say that the first, the second row and the first entry is 2, that is actually 2, 3. Okay, so now what is 2, 3? The column of that is the first column and the entry is 3. So that's the column first and entry 2 is 3. Okay, now we get another permutation, which is telling you that 2, 2 goes to 1, 3. Okay, so that is precisely this. Now the second, now we treat this as the row and column, and then we put 1, 3 in here. So we do this for every possible row and entry 1, and we get another set of entries in this, d square entries in this. And then we do the same thing with another combination. There are only 3 real combinations that are possible, that is row and entry 2. And that maps into entry 1 and column. And you get another array here. Now you may wonder, what about other things such as maybe column and entry 1, etc. But all of those just corresponds to some trivial this thing of this, in the sense that it would be just transposition and so on. So the non-trivial bijections are only these 3. Okay, so now here comes the punchline. You can do this for every array d square that you have arranged, including the identity. This would be an orthogonal Latin square if and only if all the other 2 which we are getting from this operation are also orthogonal Latin squares. Okay, so this is a necessary condition. So let me talk in terms of permutation matrices, because that's what I'll be using. So we'll represent every orthogonal, we'll have a permutation matrix representation of an orthogonal Latin square and ask what is special about that permutation matrix, which is making it an orthogonal Latin square. So here I've written out explicitly the address and the entry of that first one. So the first 2 numbers are the address and the second 2 are the entry. So that is the address, the row and column of this, and that is the entry. So wherever there is this thing, you would just put a 1 in there. For example, 2, 2, 3, 1. You would put a 1 there. Everywhere else there is 0. So this is a permutation matrix, a 9 by 9 permutation matrix, which you get from this orthogonal Latin square. And the challenge is to look at this permutation matrix and to identify whether this corresponds to a orthogonal Latin square or not. Even if you take an identity, that will correspond to an identity permutation here. That's still a permutation. But what distinguishes those permutations which are corresponding to orthogonal Latin squares? But the answer is precisely what I told you, that you can look at it every which way. If you give me any two of these, it uniquely defines the other one, makes every one of these different permutations, the permutation matrices, or rather the matrices corresponding to those Latin squares or those arrays must also be orthogonal, must also be permutation matrices. So, well, this is just one of so many possible permutation matrices. But not every permutation matrix, as I said, corresponds to that. So this is just putting whatever I said there in the language of a permutation matrix. This interchange of column with entry 1 is precisely this interchange of these indices. So now you have I alpha indexing, say this, and J beta indexing that. Then you're interchanging alpha and J. This is what happens when you are specifying the row and column, and then you have a bijection to entry 1 and a column and entry 2. So we take this permutation matrix and do something to it which corresponds to this operation, and you get another matrix, and you require that this also be a permutation matrix. And let me explain this in a very simple way. You have this 9 by 9 matrix. You construct these 3 by 3 sub matrices out of this. Let's take this block here, okay? And you take this 3 by 3 block and you put all the elements of this in a single row of 9 elements. And then, so what you're doing is you're taking this and stretching this into the first row. Of course, nothing happens. You get 1 and all zeros. But let's take something non-trivial here like this. You take this and you stretch it out into one row, and you see that the first 3 are zeros, the second 3 are zeros, and this one comes out here. Okay, so this is what corresponds to this. So this is called a realignment operation. You take this d square by d square matrix, you vectorize every sub d by d matrix of this kind, and you get a new matrix that is PR9. This also has to be a permutation matrix. Okay, in this particular case, of course, it is. So this is the realignment operation. In terms of just matrices, you can think about it as a tensor of this kind, where you're interchanging these two indices, alpha and J. The other operation, so this is written already in quantum mechanical language. So you consider I and I alpha to belong to one, I and J to belong to one subsystem, alpha and J to another, and then this corresponds to this operation. Those of you, I'll come to the connections to quantum mechanics. This is blockwise transpose. The other operation, which I mentioned, where you're interchanging column and entry 2. You're interchanging column and entry 2 corresponds to blockwise transpose. That means you take these blocks and you just transpose them. So, okay, this is actually corresponding to transpose within the blocks. So you take these blocks and then you just transpose them within the block. So this particular thing, 1 goes here, okay? And this one comes there. So you take a permutation matrix and you do this. If it remains still a permutation matrix, then you are in luck, in the sense that this is something which is going to be almost like a orthogonal Latin square. So this is known as a partial transpose operation, where you're interchanging the indices alpha and beta. Okay, so this partial transpose is also a permutation. Okay, so that's what you require. So a d square dimensional permutation P corresponds to an orthogonal Latin square of d by d if and only if the realignment and partial transpose are also permutations. So that is the summary of what I have told you so far as to how to make a mapping from an orthogonal Latin square to permutation matrices and what conditions should the permutation matrices satisfy. This is sufficient. The same, yeah.
The rows and columns. So it should also be a Latin square. Or not a Latin.
No, it won't be a Latin square. It's just a permutation of the D square, but it need not be a Latin square.
So, but the one says each one should be there only one row or one column.
That is an additional thing. That's an additional thing, right? So that's not satisfied in general. I mean, I could just write an identity kind of, 1, 2, 1, 3. So clearly it's repeating here, but of course you can, there is repetition in this, there is repetition in this, but it contains all the D square.
So I went to the 9 by 9.
Yeah.
You have this 1 and 0.
Yeah.
So it's according to your computation, you want that the condition is that each row should have only 1, 1, and each column should have only 1, 1. And there should be no 2. Is that right?
No, but if you just take any permutation matrix, then the corresponding array need not have the condition which you mentioned. If, yeah, yeah.
Is that this one, the 1 and 0 should all be, there should be only 1.
Yeah, there should be only one. Yeah.
So if you start with any matrix, do this realignment and transpose operation, what you should get back is a matrix.
Should be a permutation matrix. Then your original one will satisfy the conditions of an orthogonal Latin square. Otherwise not. In fact, it's an if and only if. So if it's not, like for instance, if you take this and do it, you will find that it's not a permutation matrix if you do that. Okay, so what is the connection of all of this to quantum mechanics? Quantum mechanics and the orthogonal Latin squares. So first of all, let me just summarize then, or think about the 2 by 2. The fact that there exists clearly no orthogonal Latin squares in these two tells us that there are no permutation of 4 objects, that is P4, such that its realignment and partial transpose are also permutations. So that's one way of proving that there's no 2 things, but that's pretty clear. And also there exists no permutation matrix in 36 dimensions because of Gary Taston and Euler, such that its realignment and partial transpose are also permutations. Okay. But every other case there exists these permutations. The question is, are there quantum versions of these orthogonal Latin squares in D dimensions, and especially do they exist for D is 2 and 6? What exactly do we mean by quantum versions? I'll come to in a minute. So let's look at this. Every orthogonal Latin square in D by D corresponds to a 4-party quantum state in this copy of Hilbert spaces, 4 copies of the Hilbert space, each of local dimension D. How we construct these 4-party states is the following. So here is A, B, C, D. So this is the address of the cell I alpha. And then you look at the permutation of this I alpha. And that is your state of the particles C and D. And then you sum up over all possible I and alpha. Okay. So this is a quantum state. After all, this permutation P is a unitary matrix. And so this is a quantum state. Now, there is a, so I hope that maybe I make this more clear. So you can also construct other quantum states such as these. I alpha, now this is for AB, you can have AC there, and you can also have AD there. You'll have three different states, they're all essentially the same state if I was to just look at this. Okay. So now, what is interesting about this? What is interesting about these states is that if we make a measurement of any two of these particles, let's say that you get 3, 2 for AB measurement, then you know for sure that the CD measurement is going to be 1, 3. So there is strong correlations between the measurements in this and this. And what is interesting is that you don't have to choose your AB or CD because of this property, which I mentioned, that there is a bijection between any pair and the others. You can choose any two parties, BC, and then, in this case, let's say AC, and then read off the entry into the other one. So this is a strongly correlated quantum state, can be constructed out of these orthogonal Latin squares in this manner. So I'll give you an explicit example later on. So a quantum orthogonal Latin square corresponds to a special four-party state. So I'm now talking about a quantum orthogonal Latin square, which has this property that you have this address AB, let's say, is in one of these things, and CD are all orthogonal states of these C and D. Okay, so psi 1, 1, etc. till psi 3, 3. They're orthogonal states of CD. Why are they orthogonal? Because if you make a measurement of AB, then you should be able to tell what is the state of the other two particles. States of quantum states which are orthogonal are perfectly distinguishable, and therefore you require them to be orthogonal. So this would be a generalization of this orthogonal, this kind of a Latin square where these are clearly orthogonal. 1, 1 is orthogonal to 3, 1 as states and so on. So this would be a generalization which could be called a quantum orthogonal Latin square, but it has to satisfy further things because this is quite trivial. You can always find 9 orthogonal states in a 9-dimensional space, and you have this. But it should also satisfy the condition that you should be able to choose BC or AD or any two of them, and you should have the same property. So for this to hold, you should have this state. You should have a state like this in ABCD, which is such that there is a unitary operator U, which is creating this bunch of orthogonal states, psi I alpha from this. But you should also have the other choices. So if you take A and C, then it should also correspond to an orthogonal set on BD. This requires that the realignment of this unitary operator also remains unitary. And similarly, with the other pair, you require that the partial transpose remains unitary. You see, so this, the conditions of an orthogonal Latin square, which we saw on a permutation, now gets translated into 4-party quantum states, which are very special in the sense that if we were to trace out any two particles, or if you measure any two particles rather, what will be left is a set of orthogonal quantum states. And for this, the most succinct way of putting this is that you need to find a unitary operator U in dimension D square such that its realignment and partial transpose is also unitary. You see, this is a natural generalization of the permutation problem when you're lifting permutations, which are also unitary operators, but into the full unitary group. Okay, so this actually specifies then 3 orthonormal bases in D square dimensions, and you can think about it like this. So let me tell you what it implies for entanglement. 4 parties, because that is the natural thing on an orthogonal Latin square, or Latin squares in d by d. So this is let's say 4 particles. Okay, here is a general state of 4 particles specified by this tensor or matrix, whatever you want to call it, Tijkl. Okay, so ijkl is some orthonormal basis, let's say the usual standard basis of these particles in ABCD. Now, if we look at the entanglement of AB versus CD, you have to construct a reduced density matrix of AB and look at its eigenvalues. Okay, and if the eigenvalues of the reduced density matrix of this are all equal, then this is maximally entangled with this. And when does that happen? So it turns out that this reduced density matrix of AB is nothing but this U matrix, which is defined like this. Ijkl is this entry of this tensor here. It's a bipartite unitary matrix. Now it's like unitary matrix acting on 2 particles, each of dimension d. If it is unitary, then clearly this reduced density matrix is proportional to the identity, and this entanglement is maximal. Now it turns out that the condition that the realignment be unitary is equivalent to the condition that AC be maximally entangled with BD. And the condition that the partial transpose is unitary comes to the case of BC being maximally entangled with AD. And that's all that's there. And therefore, this case where U is a unitary matrix such that its realignment and partial transpose are also unitary, corresponds to a case of 4 particles which are absolutely maximally entangled, in the sense that any bipartition of it is maximally entangled with the other. So this is a task of constructing absolutely maximally entangled states in quantum information. And therefore, the problem of absolutely maximally entangled state of 4 parties in arbitrary dimension D corresponds to finding these unitary matrices which are d square dimensional, which have this property that realignment and partial transpose are also unitary. So I'm not going to go into the virtues of absolutely maximally entangled states, but let me just say that they are very useful in constructing quantum error correcting codes, number 1. Number 2, there's something called parallel teleportation protocols where they are used, quantum secret sharing. So if you just, you can imagine that these are 4 parties with some shared secret, and the best way in which that secret is shared if they can share absolutely maximally entangled state. So these generalize the Bell states and the G at Z states of 2 qubits and 3 qubits into higher number of particles and arbitrary local dimension. So there is a large literature on the existence of these things. In general, it is not known, if you just give me the local dimension D and number of particles, whether this exists or not. So such a matrix, by the way, as a matter of notation, a unitary U which satisfies these properties is an example of a multi-unitary matrix. In this case, it's called a 2-unitary because it has these 2 operations, R and gamma. It's also known as a perfect tensor in the ADS-CFT community, where these are used to construct certain special kind of tensor networks. So the question going back to this is whether absolutely maximally entangled states of 4D exists. And because these orthogonal Latin squares of dimension D exist, whenever D is not 2 or 6, we also know that these absolutely maximally entangled states of 4 particles exist in any local dimension which is not 2 or 6. Okay, so at this point, I want to say that now let's start to look at the problem of whether AME 4-6 exists, because that we know does not, since there is no orthogonal Latin square of dimension 6, it's not clear how to construct an absolutely maximally entangled state of 4 particles with local dimension 6. And so in order to do that, we need to find some measure. We need to use measures, which is telling you how close you are to these absolutely maximally entangled states. So here I'm going to use these measures. They have some names. So this is called an entangling power of this unitary operator U, which is a sum of operator entangle, or actually it's the sum of entanglement in these reduced density matrices of AC and AD. So you just go back to a 4-party state. So this is exactly the correspondence which we are going to be using. Given any unitary matrix in D by D, we are going to look at a 4-party state, which is constructed from it in this manner. And then we are going to be looking at, so what we need to do is basically optimize all the entanglements in AB, AC, and BC. AB will be automatically maximal if this unitary U that you begin with is unitary. The matrix which you begin with is unitary. So we'll assume that. And then you need to only optimize these two, maximize these two. So the sum of these two is essentially what is there in these two things here. This entanglement between AC and entanglement between AD. And that is corresponding to what's called an entangling power of this unitary U. And there is another combination here with a negative sign here, which we have used in a different context, which we call gate typicality. But let me just think about these as something here, which is going to enable us to identify two unitaries or perfect tensors and to find AME46 if it exists. So, and here is an important fact that this U is 2 unitary if and only if this entangling power is 1. Okay, so we are going to try to see if U36 exists such that the entangling power is 1. It's as simple as that. Here, I'm plotting entangling power versus gate typicality, these two quantities, for the case of qubits. So D equals 2. You can see that there is nothing at EP equals 1. That is just telling you that there are no orthogonal, so AME42 does not exist. No absolutely maximally entangled state of 4 qubits exists. Therefore, quantum mechanics does not solve the problem of taking a 2 by 2 orthogonal Latin square, and however quantum you may make it, it still does not satisfy. There is no corresponding quantum OLS for the case of qubits. So in fact, this was known for some time, how entangled can two couples get. Higuchi and Sudbury, it's a very nice paper. You can, so the constraints on a qubit system are too large for this to be satisfied. But we know that absolutely maximally entangled state of 4 particles exists for Q-trits because orthogonal Latin squares of dimension 3 exist. So that is precisely the state. Here is an example of this where I'm just writing all this in one line there. Okay, so this is that. And if you look at entangling power versus gate typicality, these are local gates with 0 entangling power. This is a swap gate with maximum, with again, 0 entangling power with maximum gate typicality. But here is a gate which is in fact a permutation which corresponds to this, which has maximal entangling power. I must say that a lot of things are not understood in the neighborhood of what happens around here. So in search of this AME46, we use both numerical and analytical methods. So one of the numerical methods which we use is the following. Since we require that we require a unitary matrix with very special properties, we do the following kind of thing. So we map, there's a map from a unitary operator to the space of unitary operators defined in this simple manner. You take a unitary operator, you realign it. It's a definite permutation which is given to you. Okay, and then we do a polar decomposition of it, which is a product of a unitary matrix times a positive matrix. And this is well defined, polar decomposition of this. And what is known is that the unitary matrix which you get out of a polar decomposition is the nearest unitary matrix to M, if you do the polar decomposition of M. And therefore, you can find the nearest unitary to the realigned matrix. And then you can take a partial transpose of it. And then you do, again, the nearest unitary to that. And then you repeat this map. So basically, what you're trying to do is something which we found later is a philosophy which is known as synchron algorithms. And you're trying to optimize something. Okay, so we do this. So this is part of our numerical strategy. There is a larger class of operators which are used in many body systems called dual unitary. Two unitary is a special case of this. The dual unitary simply maximizes one of these things. The dual unitary maximizes both. So this one is only realignment is unitary. So we were looking at this because there is a huge amount of literature of many body systems built from these gates because they are solvable and so on. So in this paper, we gave an algorithm which is quite similar to this, but it did not work for DS6. It will work for DS3 and 4. And it did not work because the space is very large. And okay, here I'm just showing you some of the this kind of a thing. Although there exists no orthogonal Latin square in dimension 6, you have some permutation which comes closest to being that. That is known. And if you look at the entangling power of that, it turns out to be 0.9968, 314 by 315. So our task was to go from here to 1, whether it exists or not. So we had many interesting and false starts. Well, it's not false starts. We could go easily beyond it, 0.9968 to 0.9976 and so on. But it took a long time for us to go to 1 from that. And partly the reason was that we were applying these algorithms. So here is the optimal permutation, which is closest to being orthogonal Latin square in D is 6. If you start from that, there is a strong attractor nearby. Now you can use the language of dynamical systems, the strong attractor nearby. So it just goes there. In fact, this is a swap operator. It just corresponds to this. So, I mean, it goes to this. There is a strong attractor around A and A times swap. Many of these seed unitaries will simply go there. So there existed a seed unitary which is sitting far away, which needed some amount of thinking as to why that was the case. But magically, that seed unitary went through some kind of mountain passes, avoided these valleys, and found that, in fact, there was a U36. But this was still numerical in the sense that we have a strong idea that there is such a matrix, but we're not sure about whether this is numerical precision, 1 or exact. For this, we needed to go back and do some things which were making use of local unitary invariance, which, as you know, entanglement does not depend on local operations. So we make use of local unitary invariance in such a way that you have a unitary operator U, you can apply these local unitaries and try to simplify the matrix which you get. And this is a long story, but I'm not going to say that, but this is quite a magical thing in the sense that this kind of an algorithm led to something which you can use local operations and simplify to an extent where you're getting an exact numerical, exact analytical form of these matrix elements. And it has only, it has 9 blocks of 4x4 matrices. Okay, so it's a much more simpler matrix than a 36-dimensional matrix, but essentially it is complex. We could not make it real or orthogonal. And it has in it only 3 numbers in it, whose ratios are, in fact, golden mean and half. Okay, so it really has only 2 numbers in it. And the complex part is coming from the 20th roots of unity. In fact, the 20th root of unity comes in here essentially into this construction. So the bottom line is that indeed this solution exists, and you can arrive at this in a systematic way. Now, what this means in terms of entanglement, so we have kind of illustrated this with the help of the 4 dice. As you know, dice is it has 6 states on it, so it's an ideal system to illustrate. It tells you that if these 4 dice are made in this Ame state or absolutely maximally entangled state, you can choose at random any 2 of them and make measurements on them, and then you know what is the state of the other 2. Okay, so this is the amount of correlations which are present in this. So that is essentially what this is about. And you can go back to Euler and his officers, but in terms of the language of cards, so there are 6 now, card values starting from, I guess, 10, or no, 9. So you have 9, 10, Jack, Queen, King, and Ace, and then you have 6 other things. So now there are essential entanglements which are coming in between these entries here. So you can have something which is like a quantum version, entangled version of an orthogonal Latin square. And there are many interesting features of this, especially these states themselves, which we are constructing out of this, are maximally entangled. They are maximally entangled as qubits. And also, there are actually cliques in this. So ace, clover, king, and spade will always appear together like this. So there are cliques of this kind, and also there is a what is called a coarse grain, what we called a coarse grain Latin square structure to this, but which we later found in the orthogonal Latin square is called a frequency Latin square. So there is some underlying design to this, which we are yet to fully understand. So that's the summary is Euler's classical problem of 36 officers is indeed impossible to solve. We have not solved it. It's impossible to solve it. You have to be, and there are no permutation matrices. It's related to this, such that its realignment and partial transpose are also permutation. However, there are unitary matrices of size 36 that do have this property. And this leads to a state of 4 particles where the choice of any 2 of them renders the other 2 in an orthogonal set of 36 entangled states. As I said, there are many uses, many open problems. How many are equivalent? There is an equivalence defined in terms of local unitary invariance. We believe that this is really only one, but so we have many states numerically generated, which are Ame46. We have some techniques for seeing whether they are equivalent or not. Based on that, we conjecture that there's really only one, although we haven't shown that analytically. And of course, generalization to more than 4 parties is an interesting thing. So there's a whole field of quantum combinatorial designs, which is starting up. People have defined orthogonal Latin squares and quantum Sudokus and so on. And we hope that we have contributed somewhat towards that. So thank you for your attention.
So if there are any questions from the audience, I just want to remind you again, please use the microphone, please unmute yourself and then go ahead and ask. Yeah.
Sorry, can you show the previous, that slide? So I was trying to understand. You're saying that each entry here could have in principle been much, I mean, there are at most 4 kets in nature.
Yeah.
It could have been in principle.
It could have been more. So actually we don't, so there are only 2 or 4.
Yeah.
And actually each of them are maximally entangled. So this is not obvious for this state with 4, but actually it turns out that it's maximally entangled. Here it's clear it's like a Bell state. So yeah, so what one is writing is, one is saying that U acting on Ij is producing these, these psi Ijs, which are of this kind, which are, maximally entangled as 2 qubit states, or 2 qubit states. Oh yeah, actually it's 2 qubit. Yeah.
So another question that probably is a trivial question, but there's no way to make this unitary matrix real?
No, it's not a trivial question. We would have liked to. So the other, the other matrices which we found, like A and so on, which were doing better than the well-known, better than the classical one, they were all orthogonal. So, but this one, no. There was no way we have got many realizations of an RMA46 that look very different, but they're all complex. So I would conjecture that an orthogonal matrix does not exist, but who knows?
So somehow,
yeah, I think you need to use a field of complex numbers for this thing to work.
I have one more question.
So now in the classical case, a solution does not exist for 6x6.
Yeah.
Okay. So in this case, using some measures, you drew some graph and you wanted to know whether a particular point was approachable or not.
Right.
Could this technology be used to show that the classical solution doesn't exist? That is there an understanding of when your absolutely maximal entangled states actually correspond to a classical solution, and then say that those will not be able to approach that apex point on the right?
It's a good question. I haven't really thought about it. So the way we are defining classical is only if anything corresponding to a permutation is classical for us. Okay, because these corresponding states are not entangled. The psi ij's are not entangled. So, so for us, those are the classical. But if your question is whether some algorithm like this can produce, this is a difficult question because I think it'll be difficult because, see, here we are using algorithms which are giving us the nearest unitary. I guess in that case, you will have to find the nearest permutation. I don't know. Maybe there is a way of doing this.
If you were to stay perhaps only in the realm of classical solutions, it may be permutation, but there might be a set which is slightly bigger than classical solutions, but not quite as big as what you are permitted in quantum. And you could show that even they do not exist.
Like for instance, like for example, the orthogonal subspace. Yeah, it's a good point. We haven't tried it.
Okay.
It's possible that if we can restrict ourselves to the nearest orthogonal, which again, actually, I don't know how to do. Given any matrix, I can find the nearest unitary, but I don't know how to find the nearest orthogonal. Of course, I can restrict myself to real. I can start with orthogonal, and then I will remain in orthogonal. That I can do. And but even that, I'm not sure that we have tried that in this particular case, to start with an orthogonal and then remain in the, although actually we have, in a sense, because all of these are orthogonal matrices. So P36 is orthogonal, so it's not surprising that, so in this case, for example, it's like what you're saying. We start with orthogonal matrices, A is also orthogonal, but in fact, this W is also orthogonal. That's as far as we got. By the way, these are named after authors who got these matrices. So these, they are orthogonal, but we have not. So you can ask, what is the orthogonal matrix with the largest entangling power we have got? And there is some answer. I don't know off my top of my head what it is, but that would, we have not obviously got anywhere there.
You mentioned here that there is some sort of, like attractor kind of structures. Where are those structures?
Where are the attractors?
Where are those coming?
I don't understand your question.
You had matrices and you calculated some quantities from matrices.
It's a map of the set of matrices to itself, set of unitary matrices to itself. It's an iteration, this one here. So we can prove certain things. We can prove that, some things are easy to prove. You can prove that these two unitaries are fixed points of the map, or period 3 actually in this case. Okay, you can prove that. But whether they are the only period 3 or not, we think that is the case. So we have a recent paper which is analyzing this map analytically for the case of qubits only. So where we show explicitly the rate of attraction, exponential or algebraic and so on and so forth, if you're interested.
Maybe I can ask sort of a clarifying question. So you have a sort of a map from these matrices to themselves, define some sort of flow.
Yeah.
Is this function EP monotonically decreasing or increasing along this flow? Is that?
No, you can see that it's not.
Right. So maybe you can answer, if I can phrase the question this way, sort of, what is the connection between the flow and how this function EP changes along the flow?
Yeah. So we are interested in two questions. One is actually getting operators on this line where the realignment is unitary. These are the so-called dual unitary operators, which are maximally entangled as operators, and which you can construct interesting quantum circuits from this. So this is an extremal case. But if you're interested only in this, then something like what you have said works. We have a map, we don't have to do this partial transpose. If you do only realignment, then it turns out that this operator entanglement is a monotonic increasing function. Again, not something we can prove. We can prove only some weaker versions of it. But numerically, it seems that that is the case. So as a map, it is a very high dimensional map. It's on a space of unitary operators. So it's not a typical dynamical system, but it seems to have very interesting properties, which I think we don't know enough about. Sure.
You said that the equivalence problem question is still open, right? In D equal to 6.
Yes.
Now, what about in other T's, even dual T?
Yeah.
Are permutations the unique solution?
Good question. So again, this paper, which we have a recent paper where we show that, well, not we don't show, but there are certain things which are known. D is 3. There are some 3,000 odd orthogonal Latin squares. We can just show by just enumeration that they are all equivalent. There is only one permutation. Every other permutation is orthogonal Latin square is local unitary equivalent to that. Now, we believe, based on extensive numerical calculations and also some more recent work which is not published, that D equals 3, there is only one, even if you include the class of unitary operators. That there exists only one unique two unitary operator. However, D equals 4, we believe at this point, again conjectural, that there are infinity. So, but D equals 6 would be really interesting. So for us, we don't know, but we believe that there's only one. So in fact, Euler's, going back to Euler's 2 plus 4n, I believe that they would be special even in the quantum cases in this sense, that the number of equivalence classes might be very less or limited. But it's completely conjectural, I could be wrong. But we're also talking to some mathematicians who say that there is a way of finding out whether something is local unitary equivalent or not, but it's an algorithm which runs into, it's not clear when it will stop and how long. It's a very, it's not very clear how this is going to pan out. But I believe that for D equals 3, it should be easy, not easy, it should be possible to show with the current understanding that there is only one. Yeah.
So I think there are some questions on the chat.
Yeah, oh, sorry.
Sorry. What is the definition of nearest unitary? You kept on saying it.
It's in any norm. So you could just think of you could think of any matrix M, and then you say that you want to minimize this over the set of unitaries U, and then you go ahead and try to find some questions.
I know Latin rectangles exist. Can they be orthogonal too?
Yes, that's again an interesting question. Yes, rectangles can exist. Orthogonal, actually there will be a repetition in this case, and it depends on the ratio of the rectangle. So it has to be a multiple of the other. And this is connected, interestingly, to questions of, whatever I've talked about is for equal dimension D and D. But if you look at D1, D2, then naturally these things are useful designs. So again, that's some work in progress, but that's, yeah, they can be orthogonal in the sense of they can have exact number of repetitions. You can demand that there will be 2 repetitions along. If there is one is a factor of the other by a factor of 2, and you can demand that there will be exactly 2 repetitions. Yeah, the quantum extensions are definitely possible and interesting. They correspond to these entangled states.
Yeah, sort of related to this, my earlier question also was about cubes. I mean, if you want to have like 6 parties,
right.
Then what is known classically or even classically about them, and if at all you've thought about the quantum?
No, the quantum, I haven't thought about it, but there are some others who have thought about it. But I don't know whether there is very much known. As I said about in higher dimensions, as far as qubits is concerned, there does exist 6-party states which are maximally entangled. The corresponding classical design exists, but not. It's known that 7 and above does not exist. The quantum does not exist, so clearly the classical also does not exist. But okay, actually, I shouldn't say more because that probably will be wrong. I don't know enough about it. I doubt if very much is known. But you can look at the work of Szyszkowski, Karol Szyszkowski, one of the co-authors of mine here. They have some papers, I think 2-3 years ago, where they are talking about designs in general, combinatorial designs, and construction of quantum states from that, where they also talk about generalization to higher number of parties. Yeah. Yeah, but it looks like there is not much known even in the case of these, even in the case of squares in higher dimensions, for example, as we were discussing, the number of orthogonal Latin squares in any dimension doesn't seem to be really known beyond 9. We know that it's increasing humongously, but we don't know what happens in critical cases like D is 10.
Okay, if there are no further questions, let's thank our speaker again for a wonderful talk.
Thank you very much. Thank you for the lovely questions too.